Let's do this in. All right. This is Hamilton paths and circuits. We talked about Euler paths and circuits yesterday. For those of you guys who missed class the other day, if you go into the news feed in eLearning, I actually posted the video from the class period last time. So you can actually watch that. I posted that video already. So go ahead and watch that if you're stuck on that.
That's awesome. Sweet.
All right. Well, today we're going to cover Hamilton paths and circuits. All right. So Euler paths and Euler circuits, if you remember last time, we were trying to hit every edge on an Euler path or Euler circuit in our graph. We're trying to hit every edge. Okay, so now with Hamilton paths and Hamilton circuits, we're not going to try to hit every edge. The big idea is we're going to try to hit every vertex exactly once and never hit it more than once. Okay, so let's look at a couple definitions first. Okay, a Hamilton path that passes through each vertex exactly once. Is a Hamilton path. Okay, that's a Hamilton path. So now instead of hitting every edge, which is the Euler path, we're going to hit every vertex exactly once. So we can't go to a vertex more than once. A Hamilton path that starts and ends at the same vertex is a Hamilton circuit. Okay, so the Hamilton circuit is the only time we actually allow a Hamilton path to hit a vertex more than once, because it's going to hit, if it starts and ends at the same vertex, that means it's going to hit it. It's going to hit it twice. Okay, so that's the only time. In general, a path can only hit every vertex once, but a Hamiltonian path or Hamilton circuit can hit the one vertex where it starts and ends at the same place more than once. Okay, so let's take a look here at an example. This will help us. Just do the most basic example we can. This is one of the most basic examples we can get. Okay, if I've got A, B, C, D, and E, okay? So if I want to find a Hamilton path for this, so the idea is I want to hit every vertex once. So I could start here, for example, at A. So I've hit A. And then I could run over to B. Then I could run over and hit E. Then I could run over, hit C, run over, hit D. That's a Hamilton path. I've hit every vertex. Notice I don't have to hit every edge. Okay, so the one I just did right there is A, B, E, C, D. Now, if I wanted to make this is a path, if I wanted to make that into a circuit, guys, how could I change it? Couldn't I just add this one right here?
D to A.
Yep, I could just add D to A, and now I have a circuit, correct? So now if I go A, B, E, C, D, A, okay, that's That's a Hamilton circuit. Very simple, very simple. Now you can imagine it's not quite as simple for every problem. Okay, we have more complicated ones. All right, let's try another one. Have you guys try one? I'm going to draw something here. Okay, and put a bunch of dots here. So this is going to be A, B, C, D, E, F, and G. I want you guys to find a Hamilton path and a Hamilton circuit for this. And just go ahead and actually write your path in the comments, like, you know, something like A, B, F, C, D, G, or something like that. But remember, you can only hit each vertex exactly once, and you can't hit it more than once, except for in the case of the Hamilton circuit, where you can start and end at the same one. Okay, so that's fine, Jesse. Let's take a look here at Haley's. Let's just check it out. She wants to go C, E, A, B, F, D, G. Okay, so let's try that. So start at C, we go to D. Sorry, my bad. She wants to go C, E, A. So C, E, A. B, F, D, G. So B, F, D, G. Yep, that hits every one of them, right? Okay, that one works. Okay, and then let's try Alex circuit, because we already did a pass. So that'd be A, whoops, A, B, A, B, G, D, F, G, D, F, C, E, A. Yep, looks like a circuit. We didn't hit anything more than once, except for the A, which we started and finished at. So those both work, okay? So you can, there's a lot of different answers here, guys. There's not just one answer for these paths and circuits. There's more than one. And so those are both completely fine. Steph's, let me just check it out here. D, G, B, F, A, E, C. Yep, that works as well. That hits all of them. Good. So that was a pretty basic one. Okay. So now we're going to look at a new definition here. Okay. Whoops. New definition. Okay. A complete graph, and this is going to be important, is a graph where every vertex connects to every other vertex edge. Okay, so a complete graph is a graph where every vertex connects to every other vertex with an edge. Okay, so the most simple one that we have really is a triangle. Okay, you can see that A connects to both, whoops, B and C, right, with edges. B connects to both A and C with edges, and C connects to both B and A with edges. Okay, as a square, if I make it into a square, That is not a complete graph as it is. Because A doesn't connect to D, does it? It connects to B and C, but not D. So I need to draw this line right here to connect to D. And then I've got to draw this line to make sure they're all connected to the same thing. Make sense? So A is connected to B, C, and D right now. B is connected to A, D, and C. And D is connected to A, B, and C. So in order for a graph to be complete, every vertex has to be connected to every other vertex with an edge. All right, so now we're going to use this to kind of investigate some different options. Okay, so I'm going to delete that. Well, and I'm going to save it actually. All right, so question that comes up in graph theory: how many different Hamilton circuits are possible in a complete graph? Okay, remember I said before that there are many answers possible for these paths. So the question is, how many different Hamilton circuits are possible in a complete graph? Well, the answer is n minus 1 factorial, where n is the number of vertices. So if I have a complete graph and I want to find out how many different Hamilton circuits are possible in a complete graph, that's how many there are. Okay, let's take an example of that. That's kind of weird to look at. So let's take a look here. Let's take the very simple one we just did a minute ago, the triangle. Okay, this is a complete graph. It's complete because every vertex is connected to every other vertex with an edge. Okay, so that's my graph. So let's look at all the different, in theory, how many different Hamilton circuits should there be? Well, it should be n minus 1 factorial, which in this case would be 3 minus 1 factorial, which is 2 factorial, which is 2 times 1, which is 2. So let's just investigate. Let's do a couple of them. So if I start at A, I can go A, B, C, back to A. So that's one of them. And that one was A, B, C, A. Right? I could start at B. One, two, three. B, C, A. What was that? B, C, A, B. And then I can go to hang on a second here. I'm having some technical, it's pausing on me. C, A, B, C. Okay, but here's what's interesting about that. So the number of Hamiltonian circuits that can be completed looks like it's 3, but what did I say? It was 2. So what do you think is the give here? Anyone have a theory? Any theories on that? There's a subtlety. I wonder if anyone can fix it. Okay, here's the fix. There are 3 unique ones. Well, here's what it means by unique, and this is why I want to do this example. let's go back to the drawing board and I'll show you what I mean by unique. So I just came up with 3 seemingly different ones, right? But it turns out they're not actually different. Whoops. Because here's why. Okay, so we need unique. So unique means 2 paths are the same only on the basis of orientation. Okay. So let's start at A, for example. If I go from A and I go around like this, that's one Hamiltonian circuit. So let's write that one down. That's ABCA. The only other one there is, guys, is the one that goes the opposite direction. Because they're both the same path, aren't they? You guys see how they're both really the same path, just in 2 different directions? So that one would be ACBA. Okay, so that's what's meant. Okay, that is what's meant. So it's a complete, the book calls it repertoire of Hamiltonian circuits. So a good way to do this is we can just assume that the path begins at A and then end at A, and then find all the possible ways you can begin and end at A that are unique paths. Okay? And so there's only actually 2, because all the other paths, even the ones I start at C or B, are essentially going to be the same path, just starting and ending at a different place. So we'll deal more with this in a minute. We'll do some more examples that'll make this more clear to you. Okay, trying to find a good one here. So let's do another one that's harder to get that down. Okay, so I want you guys to try the square example. Try if you can come up. Let's figure out first how many there's going to be. Let's do that. So A, B, C, D. So first of all, there's 4 vertices in this, right? This is a complete graph because A is connected to all 3, B is connected to all 3, and D is connected to all 3, and C is connected to all 3. So how many different Hamiltonian circuits are there going to be? Well, it'd be n minus 1 factorial, which is 4 minus 1 factorial, which is 3 factorial, which is 3 times 2 times 1, which is 6. So here's what I want you to do. I want you to try to find all the different Hamiltonian circuits. And because they're all going to be similar, just start at A. Find that there should be 6 that start at A and end at A. Does that make sense? So just start with A and end at A and find the 6 different paths if you can, and try to get them to be all unique. So go ahead and try that for a second. There's a few of them from Haley. So there should be 6 of them. And so let's start working these out. You remember you got to end at A again. You got to end at A again because you're going back to A, right? It's a circuit. So make sure you put an A on the end of those, Haley. But here's the idea. So what we're doing here, guys, is that any 2 circuits, here's the big idea. Any 2 circuits that pass through the same vertices in the same order will be considered to be the same. That's why we're not starting at A and then starting at B and getting a whole different list, because they amount to the same exact circuit going in the same order, just having a different starting point. So let's go through some of these. So it looks like I could just go around clockwise here. Go like this, right? A, B, D, C. So let's just see if you guys get the same ones I do. So A, B, D, C. I can go the other way around, different order, which would be A, C, D, B. I forgot my, hang on a minute, I forgot my A at the end, yeah. Okay. Looks like I can go through the middle. I could go, whoops, I could kind of do this. Maybe do that. Right? So that would be A, D, go over to C. So go A, D, go over to C, up to B, and back over to A. So that's a new one. Now I can go A, go over to B, across down to C, over to D, and back up to A. So I've got 4 of them, right? Now I could go A down to C, up to B, down to D, and up to A. I got 5 of them. And the last one is, I think I could go A to D. I can go A across down to D, up to B, down to C, back up to A. I think I got them all. No repeats there. So it's kind of hard to get them all by process of elimination, but that should be all of them. So those are the 6 Hamiltonian paths. Again, if I start at B and end at B, I'm going to get one of the same drawings as the other ones in the same order, just at a different starting point. So it ends up being the same thing, essentially. So we're not concerned about the different starting points. So just always assume that you're going to start at the same letter and end at the same letter. Okay, that's the easiest way to do it. You said Hamilton paths or circuits. What do you mean by that? These are Hamilton circuits right here. In these exercises, we're finding circuits. This is the number of Hamilton circuits. So what I'm saying is we're trying to find all the different numbers of Hamilton circuits. Just go ahead and start. Oh, did I say paths? Okay. Well, I meant to say circuits. My bad. We want to find the circuits. The n minus 1 factorial is the number of circuits. Okay. So now we're going to talk about something called a weighted graph. Now this is where we're going to get, this is where graph theory actually gets useful in real life. Okay. A weighted graph is where each edge has numbers attached to it. Okay, so each edge has numbers attached to it. So for example, I could create a simple little graph like that. And I've got A, B, C, D, E, and F. And let's say these are cities in the state of Michigan. And I've got distances. Okay, this is 160 miles. This is 53 miles. This is 66 miles. This little distance here is 72. This one is 78. And this one is 70. So now every edge has a distance. Okay, that's called a weighted graph. So it's not just vertices and edges, but we're going to assign a weight to each edge. So what this can be useful, guys, is if I'm trying to find, if I've got to do like a sale, there's a classical problem called the traveling salesman problem, where if I've got to visit every city for my sales route, that would be a Hamiltonian path, right? Because I'm trying to hit every vertex, Hamilton path. Then I could possibly try to find what the fastest way to go through all these distances is, meaning how do I hit every one of these cities, A, B, C, D, E, and F, and minimize my distance? What route could I take that minimize that distance? Okay. So the traveling salesperson problem is one we're going to work on. Okay. The traveling salesperson. Okay. This is the problem of finding a Hamilton circuit in a complete So the graph has to be complete. Weighted graph. We just talked about what weighted is. That minimizes sum of the edges traveled. So basically, if you think of this as if these are cities and the edges, the numbers on the edges are the distances to the cities, we want to basically we want to start in Saginaw, for example. We want to hit all the cities we need to in Michigan, end at Saginaw. So that's a Hamilton circuit, right? We're beginning at the same point. We're trying to hit every city, every vertex. We're trying to minimize the distance we have to travel to hit every city. Okay. So we call this an optimal Hamilton circuit. Call this an optimal Hamilton circuit. Okay. So one of the only ways to do this, like exhaustively, all right, is to actually, like by the brute force, check every possible route and see which one's the shortest and add them up. Okay, so let's take an example of that. We'll just do a simple example here. We'll take this example where I've got city A, B, C, and D. All right. And it has to be a complete graph, so I have to have the diagonals in there so every city's connected to every other city. And I want to figure out how to get to all these cities. These cities are 190 apart. Don't trust the scale. This looks like a rectangle, but it's really not. 126. This diagonal is 155 on that one, all the way across from B to C. This diagonal is 124 across there. This distance is 157, and this distance is 179. So I want to find all the different ways to get around that. So I go back to my different routes I had before. I'm going to list them here: A, B, C, D, A, and then A. Whoops. And we're always going to start at the same one when we're trying to find all the different possible ones, because they're all equivalent, just with a different starting point. D, C, A, and then A, C, B, D, A is another one. I'm just listing all the ones from the previous 6 we found, and then A, C, D, B, A, and then A, D, B, C, A. And I'm out of room, so I'll scroll over. The last one is A, D, C, B, A. Okay. So here's what I want you to do. If you guys have your calculators out, what you basically do is you take the path like the first one, A, B, C, D, A, and you go A, B, C, D, A, and you add up all those distances of those edges I traveled along. So since we have enough people here to do it, can I get Alec to add up the A, B, C, D, A, the first one? Can I get Kevin or KJ to add up the second one, A, B, D, C, A? Bryson, would you add up the third one? A, C, B, D, A. Fourth one, Haley, can you add that up in your calculator? And if you're lost and don't understand how to add it up, well, that's fine. Just when we get to you, we'll do it. It's fine. Haley, other Haley. So Haley Huggard, do the fourth one. Other Haley, do the fifth one. And Steph, if you're still here, can you add up the last one? A, D, C, B, A. And then take a second and report those to me when you're ready. All right, so here's all the figures. Those look right. I kind of double checked them. So it looks like your best options if you're a traveling salesman would be to take this one. Or that one. That would save you quite a bit of miles, actually, almost 100 miles, over the other ones. So this is where graph theory could be a little bit useful, you know, could be a little bit useful. Okay, this method that we used right here is called the brute force method. Brute force, because it's literally called that, because you literally just look at every single path. Remember how we, in the last example, we went through how to list, you know, find out how many possible Hamilton circuits there are. Then you start with a particular vertex. As long as it's a complete graph, all this stuff only works if we have a complete graph. Start with a particular vertex and find all the different paths starting at that vertex, and you should be able to find 6 of them. And then you just have to literally list the mileage for each of the 6 and see which ones are the shortest. Okay, that is a really, really long process. So we don't always want to do that, especially if I have a huge circuit that has, like, I don't know, let's say it has 15 different distances on it. You know what I mean? We don't want to mess with that, do we? So we're going to talk about something called the nearest neighbor method. Okay, now here's what's nice about this method. The nearest neighbor method is not a foolproof method for finding the absolute shortest distance, because the only way to actually find the absolute shortest distance is to do, you know, the brute force method and literally check every route. But like I said, if there's 20 cities you're traveling to, like if we're United Airlines and we're trying to figure out, you know, how our plane can get to 20 different places, what's the best way to make the plane go through those routes to save the distance? So for example, if it's got to get to Chicago, Atlanta, LA, Seattle, and Denver all in the same day, you know, and you're planning where it's going to go from one place to the next and picking up passengers and whatnot, you're going to want to pick the shortest route that you can so that you can save gasoline for your airplane and save maintenance and mileage and all that kind of stuff and time. And so you would use graph theory. In fact, graph theory is used a lot for air traffic controllers and for people who own airlines. So my point is that we don't always care that it's exactly the smallest. So what the nearest neighbor method is going to do is going to allow us to find an approximation of the smallest. So this is the optimal path can be approximated by this procedure. So identify the starting vertex. Remember, we can start wherever we want. And then once you've identified the starting vertex, choose the edge first with the smallest weight. Travel on that one. Travel on that edge first. So choose the edge with the smallest weight. Second, next, choose the edge with the smallest weight. That doesn't take you to an already visited edge, or already visited vertex, rather. You can't go back to the same vertex twice. So as long as the smallest edge doesn't take you back to, so let's say you choose a smallest edge and it takes you back, well, then you choose the next smallest edge if you have 2 choices, because a lot of times in these graphs you're going to have 2 choices or 3 choices sometimes of which edge you take. So the last one is keep going until you're back at your starting point. That's it. It's really easy. Start start somewhere, okay? Choose the edge with the smallest weight, then choose the edge with the smallest weight as long as it doesn't go back to a vertex you've already gone to, and just keep going until you've hit every city and you've ended up at the end where you started at. Okay, and this is only going to work for complete graphs. Okay, that's really important. None of these ideas work if it's not a complete graph. Okay, so let's do an example of this. I think you'll get how this works. All right. So I'm just going to make something up here. Okay. So this is and I got to put weights on this, okay? So this is 300 miles, that arc out there. This little arc out here is 260. This little arc here is 310. This little short segment here is 152. This little short segment here is 154. This little one here is 138. This one is 120. This last one is 178. Okay, so what I want you to do there is find the use this nearest neighbor method to try to find the approximate short. Oh, I forgot one. My bad. Sorry, my phone's going off. That one's 92. Want to tell me where they started, and I'll try to run through it from your starting point. If anyone wants to just pipe in and tell me where you started on the graph, and then we'll do the algorithm. I'm not going to have you tell me what you did. I'll just do it, and you can see if you got the same answer. So what letter did you start from? Anyone? Anyone at all? No one? Come on. You're all just sleeping out there? All right, well, I'll just do it myself then. I'll pick one. So I'm going to start at the letter D. Okay? So I'm going to start at the letter D. So if I start at the letter D, I have 1, 2, 3, 4 choices of where I can go. And I should choose the smallest one. So it looks like I'm going to choose the 120. So I'm going to go along 120. Okay, so that's my first distance. Okay. And that was D.
All right.
Okay. Now I've got some choices here. This, and that I can choose from because I can't go back to D, right? Looks like
What
this.
are we trying to do again?
Well, you missed the whole explanation. We're trying to find the shortest distance through this path.
Got it.
So we always pick the shortest distance as long as it doesn't take us back to a city we've already been to. Does that make sense? So I started at city D. I go to B. The shortest looks like it's 140 right here, right?
Yeah.
The shortest one. Okay. So I'm going to go along that. That's 140. And that takes me to A. Okay, now for A, I've got 3 options. I've got this one, and that one. It looks like the 152 is the shortest one, but I don't want to take the 152. Why not?
Because it leads back to the city you've already been at.
It leads back to a city I've already been at. So I'm going to choose the 300, which is the shortest of the other two. So I go around this little 300 over to there. And that takes me to C.
92.
And then the shortest option from there is to get me to E, which is 92. And then I can either take 260. I can't take 150. I can't take 260. Why not? Takes me back to
Leads
B.
back to B. Yeah. All of them lead back to a city you've already been at.
Right. So I have now been to every single city, haven't I?
Yeah, you have.
Except
that.
for I've got to go back to where?
The main
D,
point.
because I'm a salesman, so I want to go back to where I started, right?
That's a fair point. So
So
154.
I got to go back to D. So once I've hit every city, I've got to go back to where I started right there. And that adds 154. So at the very end, I'm going to go back to the city I started at. So I'm going to add those up really quick here on my calculator. This is 120 plus 140 plus 300 plus 92 plus 154, 806 miles. Okay. Now, just so you guys know, that may not be the shortest way around. It's an approximation. Okay. So what I'm sort of interested in is, could we find a shorter route? I don't know off the cuff. I just made up this problem, but I'm going to try to see what we can come up with. We may not be able to find one. I'm trying to erase all these red marks here. Okay, so let's just take a look here. What happens if I just went, I'm just curious, if I just went around like this, if I just did that route right there, started at D and just went straight around, what does that give me?
I'll have to add all of those up.
So this would be one going over to A first, then 140, then 178, then 92 and 154. I think that's going to be shorter by quite a bit. So 152 plus 140 plus 178 plus 92 plus 154. That is 716. So actually that's shorter. I don't know if that's the shortest. There might actually be a shorter one yet. I'd have to experiment around. But this is the nearest neighbor method. So this is a shorter method, shorter route. This is the nearest neighbor route. So you have to read your directions. If they ask you to do brute force, you're going to have to list all the possibilities, which in this case would be a lot of them. They're never going to ask you to do a brute force on anything over 4 vertices. 5 would be a lot of vertices, because if there's 5 vertices, it'd be 5 minus 1 factorial, which is 4 factorial, which is 24, or 4 times 3 times 2. Yeah, it's 24 different possibilities. We're not going to ask you to do 24 different possibilities and check them all.
Right.
So you would want to use the approximation scheme, which is the nearest neighbor method, the one we just used. Okay.
All right.
So let's try another one. Have you guys try another one? I will draw it for you here.
How was your Thanksgiving break, by the way?
It was relaxing. It was good.
Glad to hear it.
It was.
I mean, mine went pretty good, except for yesterday when I had to go get a COVID test, so I'm quarantined. But otherwise,
You're
it's pretty
quarantined.
good. Yeah,
That's
because
all right.
I haven't been feeling good.
We're kind of all pretty much quarantined right now, it seems like.
Yeah.
The way life is going,
Yeah.
we're all
Oh
stuck.
boy. Sorry if it's hard for me to do a lot of the questions, because I have to switch off the tab and go to a calculator, then I have to switch back and look at it.
Right.
But that brings me to my second point. On the bright side, I'm getting my computer. I've gotten almost all my parts for my PC, and now I just have to put it all together and bring it from my dad's.
Good.
So I can finally do work a lot more efficiently, even though it's almost to the end of the school semester.
Yep. This is getting hard, so I'm gonna skip that one. I'm gonna make up a different one here. So let's go 1, 2, 3, 4, 5, 6. All right, so we're gonna go 1, 2, 3, 4, 5, 6 of them. Okay. Well, let's just do 5. Okay, so here we go. Bam, bam, bam. Put those all together. This one comes around here. And around there. And then I think I've got them all connected, right? 4, that one's got 1, 2, 3, 4. That one has 1, 2, 3, 4. That one has 1, 2, 3, 4. 1, 2, 3. So we're all good. Okay. So now I'm going to put some distances on here. This loop is 180. This loop is 360. This little wall is 98. This is 50, 128, 138, 125. This wall is 100. This little wall right here is 92. And this little wall right here is 175. Okay. And this is A, B, C, D, and then over in the corner is E. Okay. So here's what I want you to do. I want you to start at the letter B. And I want you to find the nearest neighbor route. Okay. Go ahead and start at the letter B and find the nearest neighbor route through that. Okay, let's go through it here. I know some of you guys are working on it. So let's look at starting at B. So B, I've got, all these different options here. This one, that one, this one, or that one. Looks like I'm going to choose the 98 first, right? So I'm going to go along the 98 down to here. Okay. So I start at B. That's going to take me to E, and that's going to be 98. Okay. Now my E, it looks like I'm going to choose the 50, doesn't it? That's my shortest one. That takes me to C next. That's only 50 miles. My shortest distance out of C looks like it'd be the 125 to the left there. So that gets me to D, which is 125. Okay. Now out of D, it looks like my shortest distance is going to be 92 with a 3 because I got 180, 92, and 175. So I'll pick the 92. That gets me to A. And then I've hit all of them except I've hit all 4 of them now. So I got to go back to where I started, which is the 100, right? That gets me back to where I started, B. I want to start and end at the same because I'm a traveling salesperson. I want to start in my hometown, or end in my hometown rather. Okay. And does that add up to what Haley had? Let's take a look. That will be 98 plus 50 plus 125 plus 92 plus 100 is 465. Very good.
Wow, Haley, you're just that good.
This is my route right there. Okay. So that gives you kind of a good understanding of how to do those. Okay. So does everybody understand how this works? Does anyone have any questions on this?
Not currently.
Okay. let's just review for a second here some things, okay? Some review, just real quick review. So review is, we talked about a couple things here. We talked about a complete graph. Okay. And let's just talk that out for a second. What's a complete graph? Well, a complete graph is when every vertex is connected to every other vertex, okay? All the problems we did in this section, we were dealing with complete graphs, okay? All right, we talked about Hamilton path and circuit. And the reason why, the big thing to understand about the Hamilton path and circuit is that it's different from the Euler path and circuit in this main idea, that the Euler path and circuit, we're trying to hit every edge, whereas in the Hamilton path every edge without repeating an edge, ever retracing an edge. In the Hamilton path and circuit, we're trying to hit every vertex without hitting a vertex more than once, except for in the case of the circuit where we allow the starting point to be the same as the ending point, okay? Okay, then we talked about two methods of optimal circuits, optimal circuit finding. Two methods of optimal circuit finding. We talked about brute force, which is try every of the n-1 factorial options. That's a really long, laborious way to do it, right? And what was the other way that we, the approximate way was the nearest neighbor method that we just did. And this is just approximate, it's not exact. But when we're dealing with really, really big systems in graph theory, like I've seen graph theory problems where there's 150 different vertexes, all with weighted edges, there's no way you're going to do brute force unless you have a computer program that'll do it for you. You're going to do the nearest neighbor method. Okay.
All right.
So those are all of the things that we covered today. So you guys should